We are ready to get going. So if you've been in the industry a while, you either have gray hair, green hair, or no hair. Yeah. So I'd like to introduce you to Paige Roberts, who's been around for a while. She's a techie's tech, a geek?
A geek.
Yeah, so she has an infinite interest in all things technical and has joined a very interesting company that's putting together streaming and graphs. And so she's here to talk to you about that. Welcome, Paige.
Thanks, Wayne. Let me put this thing back where it belongs. Hopefully. All right. So you guys all really kind of came here to figure out how to get better analytics by putting less data in your database. I'm sure no one is telling you that anywhere else. But here's the thing. A lot of the databases nowadays are cloud-based and usage-based, and the more you use your database, the more it costs you. So if you can figure out ways to only put the really important data into your database, then that would make your life a lot easier, right? Yes? All right, all right. But the problem is you need to cut your budget, but you also are getting inundated by a mountain of data. Everybody knows every single presentation is about how data volumes are increasing, woo. But what it really means is that you have problems dealing with the data within your budget. And you still need to do analytics. The more everybody says do more analytics, get more information, but do it with a barely increasing budget. And one of the big problems is that your tools only work on numbers. Now, unless you have a graph database, this is the way it is. It's like you have this situation where data comes in and it's an IP address that accessed a file and moved it over here, and somebody else accessed it, and then oops, it got stolen. That's an important pattern. Or you've got a company, and this company owns these assets and has this risk. And if I'm a bank and I want to give them a loan, I have to be able to analyze all that to figure out what their risk is and how much I should charge them for insurance. These are all things that are not numbers. These are things. This is a company, this is a person, this is an IP address, this is an entity, an actual thing. And that's categorical data, which if the data is categorical, the state of the art right now is to spend a bunch of time processing it, turning it into this big, ugly, wide, sparse numerical data set, and then you can do analysis on it. Now, the only thing that lets you skip that is the graph database, but it's still, then you have to convert it all into a graph and put it into a graph and do only this specific type of analysis on it, because that's all it does. And your regular database, it doesn't help. You still have all the things you have. So what it really means is you end up with too much data to analyze all of it. A lot of it is low value, especially if you're trying to deal with machine data. If you're trying to monitor it in real time, you get all these false positives and people get fatigue and they just stop paying attention. You end up with a big problem that affects your budget, among other things. So what the big problem is, you have more and more data to analyze, and your budget isn't as increasing as fast as the data. That's pretty basic. But what does that mean under the covers? It means web clip streams, call center data, call detail records if you're in the telco industry, all the things, every single industry has all these human-generated data streams. But here's the thing. Machines in one day generate more data than people in a year. So even though this Twitter fire hose and all the things that people are talking about are really big, the IoT, the machine data, the sensor data just dwarfs that. Just the mountain of data is insane. And people talk about that being low value data. Well, I mean, if you wanted to pull out one single record and look at one reading on a sensor, yeah, that's pretty low value. But if I'm dealing with a supply chain and my sensor is measuring temperature and it says 35 degrees, 35 degrees, 35 degrees, and then all of a sudden it says 60 degrees for an hour, and then it goes back down, 35 degrees, 35 degrees, my food's ruined. What I was trying to transport, it's gone. But I have no idea unless I had those sensor readings and that particular needle and the big old gigantic haystack of readings is very high value. That is money. That matters. And the same thing is true of pretty much any machine log. For network optimization, for finding cybersecurity threats, for the SCADA streams. I don't even know how to say that, an acronym, but what it is the control of all your devices, all the information they're giving you so that you can monitor them and control them really well. It's a lot of information, but it's really important that you be able to analyze it, where things are, all of that. So what's the real challenge? The real challenge is one, it's too slow. If you dump everything into your database, or your data lake, or your data lake house, or whatever you want to call it, if you dump it all in there and then do the transformation, the deduplication, the cleanup, all of that, and then pull out the important things, and then do your analytics and convert your categorical numeric, if you're lucky, that's going to take you a few hours. Chances are we're talking days. And you get unhappy customers because they're really expecting it to be a lot faster than that. Your fraud detection is the best you can do. I find out 3 days later that somebody stole a bunch of money from me, as opposed to finding out when it's happening and stopping them from stealing a bunch of money from me. Your cyber intrusion, you find out that somebody came in and stole all your data after it's all gone. That's a problem. You need to be able to do that as they're stealing it and catch them and stop them before they get it out of there. And your machine alerts. It's like I get all this mountain of false positives, or I get just a mountain of data, and somewhere in there there's something important, but trying to find it is half the problem. So too slow, that's one of the problems. And the other one is the signal is drowning in the noise. There's just too much data that isn't important. And I'm trying to, all the database vendors are saying, put everything in the database and then do something with it, which, you know, is great for their bottom line, but not so great for you to figure out what you need to figure out before the time limit goes up. So you need to figure out how to train your machine learning algorithms more effectively. So you need more focused data. You need to figure out how to take duplicates from the multiple systems that are sending you data and figure out that J. Smith here and J.W. Smith and John Smith and these three different are all the same guy. Before you stick 3 different records into your system, you need to be able to figure out who's who, or J.W. Marriott and Marriott, and so 3 different companies. It could be any kind of entity. And of course, the mountain of machine data, pull out the really important stuff that is high value and throw away all that hay that really you don't need. So there's two ways that you need to do this to address these 2 challenges. One is you got to do it faster. You got to accomplish what you're trying to accomplish in less time. That's pretty simple, right? So right now our system is data streams in, we maybe do a little bit of event processing on it, we dump it in our data lake, our database, our data warehouse, whatever it is, we do the data transformation, the entity resolution, the finding whatever is important, the converting our categorical data into big wide numeric data to train our algorithms, all of that. And then you can train your algorithms, or you can do your analytics, or you can find your entities, you can figure out the things at the end. And if you're lucky, mean time to answer is hours. What we need to do is shift all of that left. Do as much as possible in the event stream as the data is coming in before it ever hits your database. That will help both your bottom line, because you're no longer paying for as much data, and it will give you an answer much more quickly on the things that need that super speed to be useful. So the other thing you need to do is you got to boost the signal. So what's the best way to boost the signal is to filter out the noise. So if I got to refine my data, what I need to do is figure out where are my duplicates, which sensor readings are unimportant, find the things that are really important and put those in my database. Another thing that's really helpful is instead of having to convert all that categorical data into something that's bigger and uglier and harder to analyze and takes longer, just analyze it in place and get the answers you need and put those in your database. So what we're looking at is feature extraction for your machine learning, complex event processing, entity resolution, anomaly detection, finding that needle in the haystack, which is sometimes made of gold, or sometimes it's really dangerous and can stab you in the butt. So either way, you need to find that and get rid of all the rest. So there's a couple of ways to do this. One way is the graph concept. Now, I think it's in the database world and you think everything has to be tabular. You sort of think graph is this weird thing that's off to the side that only specialized certain people use. But the thing is, a graph can represent anything. It can represent two companies and their partners. It can represent two machines that are networked. It can represent this guy is a friend with this guy who is a friend with this guy, and that guy might be a fraud actor. There's a lot of different things that you can use this for, but the big thing that it is good at is categorical data. So entities, people, things, you can represent anything, but if it is a thing and it has a relationship to another thing, that makes it ideal for graphs. But graph databases are slow, and one of the things we need to do was speed it up. So what we came up with was this thing called Quine, which is an open source capability that does streaming graph. And essentially what it does, the problem with existing stream processors like Flink, and there's several others that are really good, the trouble is they have these time windows. So let's say I'm a country and I want to invade your important network. What do I do? Well, there's a lot of ways to get in, but the thing is, getting in is only half the problem. Then getting what I want out or doing some damage, that's like the other half. So the first half is getting in, and there's the concept of an advanced persistent threat, which is a person who gets in and then waits. They don't do anything. They just sit there until all the time windows on all the cybersecurity software, every event processor in the world slides off. And now that first half of the pattern that you need to find in order to know that this is a cybersecurity threat is gone. Your time window has gone past. That's the end of it. We have no idea that happened. So when they start stealing data, they look like legitimate users. This is what makes advanced persistent threats very hard to find. Well, DARPA, who is our research branch of our government, went in and said, this is bad. We need to develop some tech to fix this. So they developed Quine, our open source capability. It is an event processor based on graph, which has no time windows, which means I can find a pattern between entities and relationships and all of that, between something that happened 3 years ago, something that happened last week, something that happened a microsecond ago, and something that maybe won't happen until next week. And I can look for that pattern, and the moment it happens, I immediately have caught who I need within a microsecond. And this thing keeps going to sleep because it thinks I'm not doing anything. All right. So that's the general idea, being able to do event stream processing of categorical data as it goes along. So in 2022, they came out of DARPA and were launched, and Quine open source now has thousands of users. But if you need to scale beyond 1,000 events per second on per CPU on a single machine, if you need to cluster base that, that's what that .streaming graph is, the commercial version of that. So what does it do? So current event stream processors, if you're trying to find a pattern, They look for joins. They try to put things together to find that pattern. And the trouble is that they have to store the data intermittently in memory. So your memory gets overloaded. The way that it's storing data is not ideally suited for this particular type of analysis. And it kind of, you end up with way too much stuck, and then the time window slides by, and then it can't find that first part. It's gone. So one of the things that Quine does is there's no time windows, so you don't lose anything. The semantics are easily updated. It's designed for categorical queries so that you can find what you need to find. And that's pretty much it, the ability to do streaming graph. So Quine is the open source version. Streaming graph is the commercial version. If you need to cluster base it, you need commercial support, all that. Novelty is kind of cool because it's a self-learning anomaly detecting AI built on top of this. So you can just give it your data. You don't have to label it. You don't have to do anything with it. You just hand it your data. It figures out the context from the data and tells you which things are important, anomalous. You don't even have to know what the pattern is. It will figure it out itself. It's great for unknowns. And that's pretty much how it works. The data streams in. You have an ingest query that figures out how to turn all that data into a graph. And the graph stays in memory and changes over time, becomes richer and richer. And you define queries of the pattern that you're looking for in that graph, and it will find them within a microsecond. Even a really long query that looks at something 3 years ago takes 3 microseconds. And it immediately goes into a Kafka stream or some other stream, and you can put it in your real-time monitoring to get real alerts that matter. You can put it in your machine learning. You can take a snapshot, do graph neural networks to train your machine learning models. There's a lot of different things you can do with it. But the idea is you can get that speed, and you can do the kind of analysis that normally takes a graph database. And it's pretty much a very new tech, very new company. And I would not expect you to have ever heard of it. But the nice thing about it is you can take that mountain of data, narrow it down to what's really important, and only put that in your database. So that's kind of the idea. I've got about 5-10 minutes for questions if anybody is wondering what the heck am I talking about. Because this is pretty new, and I realize that a lot of people have never heard of it before. So anybody got a question? Sure, go.
I get it in the abstract. Do you have something more specific as an example?
Well, the first one, of course, is advanced persistent threat that I think of, but what's your area so I can give you one that's more relevant?
Data warehouse.
Data warehouse, well, data analytics. Essentially you can do streaming data refinement. You can do what they used to call real-time ETL, except that ETL is such a, last century term that nobody uses anymore. Take out the noise, put the signal straight into your database, get your answer faster, reduce your budget. That's kind of the idea of that. I think I gave some examples of entity resolution, machine learning. If you've got a mountain of data and you need to find the things that are important, it can locate those and give you the keys. If you want to train a model, machine learning models require a fairly balanced data set where you have a certain amount of everything is fine and a certain amount of this is what I'm looking for that's unusual, so that you can train it on what's an okay thing and what's not an okay thing. So it can recognize the not okay thing even when it comes after 100 okay things. But what that means is if I just give it the existing data set, it won't be able to train. You can't train a model on that. You have to filter out a lot of the things that are just not really a problem. And if you put it straight into your database, then your database has to do all that work. And it takes time. This can do it much quicker. And you can ask different questions if you want to before it ever goes into your database. And say, what's important? And only put that in there. Anybody else?
So
Yeah. So yes, absolutely. You could do both simultaneously even. But one of the things I think that was really cool was one of the large banks, who I can't name yet, had a repository of the last 5 years of data that their human experts had watched in order to find fraud. And everything that they had flagged as possibly fraud, they just fed it into Novelty, which is our AI, and it found all of the instances of fraud that the human experts had found, plus several that they'd missed. So that's kind of, it gives you that advantage of being able to find unusual things, and just because something is unique doesn't mean it's really all that weird. In some cases, that might be perfectly normal to have, I don't know, something only connecting to this IP address once. That's not that big a deal. But if it's genuinely anomalous, if this is genuinely a problem, it will find it. And that's pretty amazing. That, and it'll do it within microseconds. In this case, 5 years of data. There's another thing that a lot of people ask me, I'm surprised you guys haven't. It's all in memory, and it's looking at years of data. It doesn't have a time window. How does it do that within a microsecond or two? And how much beefy RAM do I need to make it work? The answer is we have done demos of the open source software on Raspberry Pis, the smallest Raspberry Pi they make. This software is designed to be very low resource hog. So you can do it in usually 150 megabytes of memory. When it really maxes out and it's really working hard, 300 megabytes of memory, which is more than you probably have on your phone. So it's pretty nice that we did a test on large clusters with 1 million events per second. And we discovered that if you use the cheaper, smaller clusters, smaller machines in the cluster, you can actually get the same performance. You don't need a beefy RAM machine to make it work, if that makes any sense. Anybody else? Still got to come. I'm a little early. Wow, I went through that really fast. Much faster than I did when I was practicing it. All right, so if everybody's cool, we've got a guy from Denodo who is coming up next, and I need to like switch everything over. So if anybody has any questions, please ask me.